All right, so for today's lecture, the only thing that we were going to do was work some more example problems regarding the transient analysis of RL and RC circuits. Before we work the in-class assignment for today together, does anybody have any questions about previous in-class assignment problems or any of the homework problems or anything like that?
Yes, in class assignment 15, the first one.
All right. So this is the problem that you asked to look at. So we're going to follow the steps, analyzing the circuit at t is equal to 0 minus, 0 plus, and infinity. Then we're going to determine our time constant, and then we're just going to plug stuff into our generic equation. Okay. So let's see here. We are ultimately trying to find an expression for our inductor current and our resistor voltage. So over here on the left, I guess, um, I'll redraw our circuit at t is equal to 0 minus. So at this particular point in time, the 12-volt source on the left is disconnected. So we have our 12-volt source over here, open circuit representing our switch. Here we have a 2 ohm resistor, an additional 12-volt source. Here is our 4 ohm resistor. Our inductor is going to look like a short circuit because t is equal to 0 minus represents a time where we're at DC steady state. Here is an additional 2 ohm resistor. And the quantities that we are interested in are this current right here, which will be IL at 0 minus, and this voltage right here, which will be VR at 0 minus. So a couple of things that we can observe here. The first of which is that this 12-volt source over here on the left isn't fully connected, so it's not going to do literally anything. And the next observation that we can make is that the 4 ohm resistor, which is in parallel with the inductor, is essentially shorted out at t is equal to 0 minus. So this path isn't going to do anything either. So taking both of those things into account, um, we could either do voltage division to find VR and then use that to calculate IL, or we could use Ohm's law to calculate IL, and then Ohm's law again to calculate VR. I'm going to do voltage division. So I can say over here that VR at 0 minus is just going to be 12 volts times 2 ohms over 2 ohms plus 2 ohms is 6 volts. And from this piece of information, we could say that IL at 0 minus, so all of our inductor current is going to flow down through the 2 ohm resistor that we just took the voltage drop over. So it's going to look like 6 volts divided by 2 ohms is 3 amps. Before we move on to our analysis at t is equal to 0 plus, does anybody have any questions about the analysis that I did here? All right. So at t is equal to 0 plus, I'm just going to edit this guy. Our inductor is no longer going to look like a short circuit, and our 12-volt source is now connected over here. So what should we be replacing our inductor with at t is equal to 0 plus? Does anybody remember?
3 amp. amps.
3 amp current source, and it'll have the same direction as IL is defined as well. So this tells us essentially IL at 0 plus must be IL at 0 minus, which is 3 amps. And so the only thing that we really have to solve for is that voltage VR. So what I'm going to do is essentially nodal analysis, but it's not really nodal analysis because that would kind of be overkill. So I'll explain what I mean by that in a second. So I'm going to apply Kirchhoff's current law at this node right here. And it's actually the only node that I need to write a KCL equation for. So I'm just going to add this current plus this current plus this current together, and they should be equal to 0. Well, the voltage at this node is literally just going to be the VR at 0 plus that I'm looking for, because the positive polarity terminal of VR is at that node, and the negative polarity terminal of VR is at ground. Okay. So my KCL equation is going to look like negative 3 amps plus VR at 0 plus minus 12 volts, because the voltage at this node right here is 12 volts with respect to ground, because there is a 12-volt source between that node and ground, divided by 4 ohms, plus VR at 0 plus divided by 2 ohms is equal to 0. And now I'm going to throw that one equation, one unknown thing into the numerical solver of my calculator. So that's going to look like negative 3 plus x minus 12 over 4 plus x over 2 is equal to 0. And now my calculator is thinking about what that result is going to be. Still thinking. So I got the result of 8 volts. Just going to double check that equation real quick. So negative 3 amps makes sense. That's the current flowing up. The current flowing to the left through the 4 ohm resistor is VR minus 12 over 4. Current flowing down is just VR over 2. All right. So does anybody have any questions, comments, or concerns about the analysis that we did here at t is equal to 0 plus?
So you essentially just chose, since it was ground and you only needed one variable, you just found it by instead of doing the whole analysis.
Well, if we had bothered doing the whole analysis, essentially what we would have found, so let me color in this green node right here, right? So this guy would have been 12 volts with respect to ground. And this guy right here would also be 12 volts with respect to ground. So there's no other KCL equation for me to write, even if I do the full nodal analysis procedure. I
Yeah,
would
you're
have
correct.
those two voltage relationship equations and then KCL over there. So, all right, let's look at what's going on at t is equal to infinity now. And I'm probably going to need to just erase this whole thing, since it's getting too busy with annotations and everything. Make my life slightly easier. Okay, so at t is equal to infinity, our switch is closed and our inductor is going to look like a short circuit again. So we should have something akin to this. So 12-volt source, 2 ohm resistor, an additional 12-volt source, 4 ohm resistor, short circuit across the top of the 4 ohm resistor because our inductor looks like a short at t is equal to infinity. And here is another 2 ohm resistor. This is IL at infinity, and this is VR at infinity. We should be able to observe that yet again, the 4 ohm resistor isn't going to do literally anything because it's in parallel with the short circuit that is representing our inductor in the top right. Now I'm trying to decide if I want to do nodal analysis here. But that won't work because I don't know what IL is. So that'll give me, well, I'll have to have a full system of equations. I'm trying to think if there's an easier way to do this. So like one thing that's obvious to me, but may not be as obvious to you, is that the voltage at this node right here that I just colored in green. Actually, let's keep on doing that real quick. Okay, so VR is 12 volts by inspection. If we choose the bottommost node as ground. Okay. And let me make this guy right here orange. Another thing I know is that this guy right here is 12 volts, which means since there's 12 volts on both sides of this 2 ohm resistor, there's no voltage drop across this resistor, and so there's no current flowing through it either. So we can see essentially by inspection here that VR at infinity is 12 volts, and then IL at infinity is going to be 12 volts divided by 2 ohms is 6 amps.
Why is there
And
no current flowing through the 2 ohm resistor?
it's got 12 volts on both sides. So what's the voltage drop? 12 minus 12 is 0.
Yes, sir.
I'm just double checking everything. So I have that one big top node and then the bottom node and then just that one smaller node between the 12 and the 2 ohm resistor. So I feel like that seems legit. Um, if we wanted to do a more formal nodal analysis for this guy, we could, but I think we'll wind up getting the exact same results. Actually, we can't do a more formal nodal analysis because we have 2 supernodes, each of which touch ground. So really, if we wanted to do this a different way, we would have to wind up doing mesh, which I'm just going to trust that I'm right. So now let's look at finding our time constant. So hopefully it is very obvious that our equivalent inductance here is just going to be 2 Henrys because it's the only inductor in our system. So that means we just need to find REQ. So these terminals up here are where my inductor was. So I'm going to be looking into this. So here's my 4 ohm resistor. Here is a 2 ohm resistor. My 12 volt source is shorted out. This 12 volt source over here, switch closed, is also going to be a short circuit because I'm just turning those independent voltage sources off. And then lastly, I have a 2 ohm resistor over here. So if I look at my nodes, I believe what I see is 4 in parallel with 2, right? So this 2 ohm resistor right here is shorted out because it's touching the green node on both sides. So I see the 4 ohm resistor between green and red and the 2 ohm resistor between green and red. So that's going to be REQ is 8/6. Goodness, that's too thin. So 4 ohms in parallel with 2 ohms. 4 times 2 is 8/6 is 4/3 of an ohm. From this, tau is LEQ over REQ. So let's see. So 2 divided by 4/3 is the same thing as 2 multiplied by 3/4. So that's 6/4 is 3/2 of a second. The inverse of tau is then 2/3 per second. And I now have everything I need to just plug stuff in. So let me just do it over here. IL as a function of time is going to look like 3 amps for t less than 0 minus, and then it's going to look like 3 minus 6 is -3 e to the negative 2/3 t plus 6 amps for t greater than or equal to 0 plus. IR as a function of time is going to look like 6 volts for t less than 0 minus. 8 minus 12 is -4 e to the minus 2/3 t plus 12 volts for t greater than or equal to 0 plus. And that's correct. Joseph, did my solution, I don't know, help at all, or did I go through it too quickly?
No, it helped. It was the last bit of the second step and the beginning of the third that got me. So
Okay. Does anyone else have any questions regarding any ICA problems or homework problems or anything like that? All right. Well, then look at this guy. Oh, did not realize. I think I probably need to upload the unedited version of this for you guys. I'll do that in a little bit. But essentially, this is ICA number 16. And this is probably the hardest problem, or one of the hardest problems that you guys will have seen before you get to homework set number 15. Let me talk about that really briefly, actually. I'm going to bring homework 15 up on WebWork really quickly. So this problem is actually fairly similar to the ICA problem. The ICA one is a little bit harder because it's got 2 inductors that we'll have to deal with, but nothing too wild or crazy here. If we look at this next problem, this is a horrifying mess of bullshit. Looking at problem 3, not too bad. Problem 4, also not too bad. I don't know why. I seem to remember this one being much, much worse. So what I've done in the past and what I intend to offer to you guys as well is because I just really hate this homework assignment. just because it seems more in line with practice on nodal and mesh than it does actually dealing with the transient analysis stuff. It's going to wind up being a bonus if you choose to do it. So when I calculate your final homework grade, I'm not going to include any points from this homework set at all into the total number of points available for homework. So if you choose to do this one, it's literally just a bonus. I'm of the opinion that all practice is good practice, but especially with problem 2, I guess, where it's just a big, huge, ugly circuit that really doesn't reinforce the transient analysis stuff at all, it largely seems like a waste of your time. So anyway, so let's get back to the ICA. So we're given the following circuit, and the only thing that we're interested in is the voltage drop across the current source as a function of time. That being said, we do have energy storage elements, so we are going to have to pay attention to what's going on with them. So the first thing I want to do is look at this and see if there's any simplifications that I could potentially make. So if I identify all of my various nodes for this problem, I can see that I have several nodes. None of my resistors can be simplified currently, but you'll notice that my 3 Henry inductor and my 1 Henry inductor are connected in parallel because they're both between the green node in the kind of middle right and the pink node on bottom. So what would a 3 Henry inductor in parallel with a 1 Henry inductor look like?
3/4.
3/4. Absolutely right. Or 0.75 Henries. So I'm going to choose to replace both of those inductors with a single inductance having a value of 3/4 of a Henry. Okay. So I'm going to choose to do that by essentially erasing these guys and then just putting in a 3/4 of a Henry inductor between the green node and that pink node. And for what it's worth, we've accidentally jumped forward and found what LEQ is for step number 4. Okay. So I've made that simplification, and I intentionally didn't ask what was going on with either individual inductor because there's really not a good way to determine how any current is going to split between those two inductors when we're at DC. Later on, when we're dealing with sinusoidally excited circuits and we're dealing with what's called impedances, we can just use current division relationships to figure out what's going on. But because we're at DC and both of those inductors are behaving like short circuits, we really can't do anything unless we lump them together. Okay. All right. So I need to know what's going on with my inductor current at a minimum at t is equal to 0 minus so that I know what's going on in later steps. So I'm just going to choose my inductor current to be flowing diagonally down and to the right, like so. And now I'm ready to start my analysis. So let's look at this circuit at t is equal to 0 minus. Oh, Jesus. I did not realize I had already left this stuff up here. That is Well, goodness. So I must have accidentally overwrote my assignment sheet with the solution earlier, but that's fine. So this is what our circuit would look like at t is equal to 0 minus. And it looks like the last time I worked this problem, I did it using superposition. So essentially, with that 5 amp current source off, we just see the 10 volt drop being applied over two 4 ohm resistors in series. And so the voltage drop across either of the 4 ohm resistors is just half of 10 volts. And then with the voltage source off, we see the current splitting up between two identical 4 ohm resistors. So that's where that 5 amps over 2 comes in. And then multiplying that by 4 ohms gives us the voltage drop of a total of 15 volts. And then I used Ohm's law to calculate the inductor current, which is just the voltage drop across the 4 ohm resistor divided by the resistance of the 4 ohm resistor. I'm going to delete the second page of this thing so that we can actually work this stuff out in a moment. Does anybody have any questions about the analysis I did, I guess, last quarter for t is equal to 0 minus?
Where did the 10/2 come from?
So if we do superposition, let me redraw the circuit with only the 10 volt source on, right? So here's the 10 volt source. Here's the 4 ohm resistor. Here's a 4 ohm resistor. This is our inductor, which looks like a short circuit. My current source is turned off because I'm doing superposition. And this is VCS at 0 minus. Okay. So I see 10 volts being divided evenly between two 4 ohm resistors. So the contribution of my voltage source to the quantity VCS at 0 minus is just 10 volts over 2 or 5 volts. Was that sufficient? Effectively, I'm just doing voltage division, and because there's only two identical resistors, the voltage just divides in half.
I see. Yes, sir. That makes a whole lot more sense now.
Yeah. Okay. So now let's analyze the circuit at t is equal to 0 plus. Let me, I guess, give myself an additional page here. And I just want a blank page. All right, so at t is equal to 0 plus, our switch is closed. So we should have something akin to this. So here's my 10 volt source. Let me scroll up here, okay. 4 ohm resistor. Five amp current source across which we're going to have VCS at 0 plus. Here's another 4 ohm resistor. This guy diagonally across is going to be my inductor. Let me scroll back up here. So I've got 6, 12, closed switch. Let's see, that current should be 15/4 of an amp. All right. So if you guys have the ICA from Canvas, you already know how I solved this problem. I guess it was last quarter. So I'm trying to decide if there's a way that we can do it different just for the sake of being different. I feel pretty strongly like I probably did nodal analysis, so let's throw mesh at it and see what happens. Yeah. So I'm going to call this mesh current I1. This will be I2. This will be I3. This will be I4. We have two current sources. So we're going to have one current relationship equation that tells us that 5 amps is going to be I4 minus I1. We have another current relationship equation that tells us 15 over 4 amps is going to be I4 minus I3. Then we're going to have our super mesh equation. So our super mesh is going to be around this path. Like so. So that would give us negative 10 volts plus 4 ohms times I1 plus 4 ohms times, let's say, I4 minus I2 plus 6 ohms times I3 minus I2. And I'm running out of space here, so I'll just keep adding over here. 12 ohms I3 is equal to 0. And then we'd have our KVL around mesh 2 equation. So that's going to look like 6 ohms times I2 minus I3 plus 4 ohms times I2 minus I4 is equal to 0. And so now I'm going to grab my Casio 991 that can do 4 equations, 4 unknowns, so that I don't have to bother with MathCAD here. And I'm just going to solve this guy. So in my first equation, my coefficient for I1 is -1. My coefficient for I2 is 0. My coefficient for I3 is 0. My coefficient for I4 is 1. My constant term is 5. In my second equation, my coefficient for I1 is 0. My coefficient for I2 is 0. My coefficient for I3 is -1. My coefficient for I4 is +1. My constant term is 15 over 4. In my third equation, my coefficient for I1 is +4. My coefficient for I2 is -4 minus 6. My coefficient for I3 is 6 plus 12. My coefficient for I4 is +4. My constant term is +10. And in my third equation, my coefficient for I1 is 0. My coefficient for I2 is 6 plus 4. My coefficient for I3 is -6. My coefficient for I4 is -4. My constant term is 0. Solving this system, I got I1 is negative 5/16 of an amp. I2 is positive 39/16 of an amp. I3 is 15/16 of an amp. That 5 looks like garbage. And I4 is 75/16 of an amp. So knowing those four mesh currents, can anybody tell me how we might solve for VCS at 0 plus? So what if we just wrote a KVL equation around mesh 1, right? So if we were only dealing with mesh 1, we would have negative 10 volts plus 4 ohms times I1 plus VCS at 0 plus is equal to 0. So VCS at 0 plus would be equal to 10 volts minus 4 ohms times I1, where I1 is negative 5/16 of an amp. So that would look like 10 calculators acting up. So 10 plus 20/16 is 45/4 volts, or 11.25 volts, which should be the exact same thing I got using nodal analysis, I guess, last quarter. Okay, now we would analyze the circuit at t is equal to infinity. So at t is equal to infinity, our circuit would look something like this. So here's our 10-volt source, 4 ohm resistor, short, another 4 ohm resistor. Our inductor is a short. Here's a 6 ohm resistor. Here's a 12 ohm resistor. Five amp current source across which we're trying to find VCS at infinity. And let's see. So I'm going to identify my nodes here really quickly. So I've got this blue node. Let's do this guy over here in green. And lastly, let's put this guy in red. So I can see that I have 4, 6, and 12 all in parallel together between my blue node and my green node. So this could be considerably simplified to look like a 10-volt source in series with a 4 ohm resistor. Here's my 5 amp source across which we have VCS at infinity that we're interested in. And then over here is going to be those 3 resistors in parallel. So let's see, that would be 1/4 plus 1/6 plus 1/12 looks like 2 ohms. If we were so inclined, we could do superposition here, but that's probably unnecessary. I think we can get it done just using KCL at this node right here. So flowing up, we have VCS at infinity minus 10 volts over 4 ohms. Flowing down, we have minus 5 amps. And then flowing to the right, we would have VCS at infinity over 2 ohms is equal to 0, where I'm essentially treating that bottom node as ground. So I've got a 1 equation, 1 unknown system. So I'm going to use my numerical solver to take care of that for me. So let's see. X minus 10 over 4 minus 5 plus X over 2 is equal to 0. Calculator's thinking. Got 10 volts there. I'm just thinking about that really quickly. No, my equation's right. Okay, I was trying to think if there was a reason why, in particular, essentially no current flows through the 4 ohm resistor, but I guess it just works out that way. So the last thing that we would need to do, unless anybody has any questions about the analysis I did there, or the simplification and then the KCL expression, would be to find the equivalent resistance of our system since we've already found LEQ way back at the beginning. So to find the equivalent resistance, we turn off our 10 volt source. Here is our 4 ohm resistor. We turn off our current source. Here is another 4 ohm resistor. We're doing this during the transient condition, so our switch needs to be closed. Here's a 6 ohm resistor. Here is a 12 ohm resistor. And then we're looking in through this set of terminals to find REQ. So I'm going to identify my nodes. So we've got that guy. That guy. And this guy. So between the pink and the green, so I'm going to have 4 in parallel with 6. Now I'm at the blue node, and between blue and green, I have 4 in parallel with 12. So 24 over 10 plus 48 over 16 is, let's see, 2.4 plus 3 is 5.4 ohms. Yep. And so from this, our time constant is 0.75 henries over 5.4 ohms, which comes out to be 0.138 repeating seconds. And then the inverse of tau would be 36/5 per second. So from this, the voltage drop across our current source as a function of time is going to look like 15. And then let's see, 11.25 minus 10 is 1.25 e to the negative 36 t plus 10 volts for t greater than or equal to 0 plus, which is indeed correct. Okay. This is our third day on this material. I am more than happy to continue working example problems if you guys want me to. I'm also totally fine if we call it here. What would you guys prefer? I've bored you all to sleep. Awesome. Thank you for replying, Trevor.
I'm good. I'm good to work web work problems.
Okay. Well, I will hang out on Zoom if you have any questions about any of the web work problems or anything like that. If not, enjoy the rest of your afternoon.
I have a question about the test next Monday. Is this the last of the material on the test or?
Yes. So
Okay.
the material that we're going to cover on Wednesday and Friday of this week, which if I'm remembering correctly, is based on operational amplifiers, is the first material that is going to show up on exam number 3. Trevor, you can if you want to. I'll probably wind up just throwing this ICA out since I accidentally put up the solution instead of the actual thing. Yeah. But anyway, so exam two's material starts with Thevenin and Norton equivalent circuits, and it ends with this transient analysis stuff. So realistically, it's only on 3 topics. Thevenin and Norton equivalent circuits, capacitance and inductance, and then transient analysis. For the transient analysis problems, if you look on the old practice tests and stuff like that, effectively, I broke those problems down into multiple parts. I still intend to do exactly that for you guys' upcoming test. However, there is going to be slight differences between each of the steps, meaning that I might slightly change resistor values or something like that. And then I will provide you with information from the previous steps so that if you mess up on the first part, you don't miss 4 or 5 problems in a row, because that was unfairly brutal to you guys. So each individual part will essentially be its own kind of little problem, and then I'll provide you with the information to tie everything together at the end. So I'm trying to improve scores by, not having everything reliant on previous steps.
Did we ever figure out about our test 1 stuff, Dr. Harmon?
So it is my intention to get up a kind of second crack at exam 1, essentially for bonus points at some point tomorrow for you guys. And it will be due in like a week or something so that you have plenty of time to work on it, but not stress about it. So essentially, I'm going to write out a brief, I say brief, like 20 problem test type thing. Throw it up on Canvas, and then you can make up to 40 bonus points towards your exam 1 score. As I said a moment ago, it's my goal to have that available to you all by tomorrow. When I have it closed, I'm thinking about having it closed early next week, but I also want to make sure that you guys working on it doesn't impact your studying for exam 2, so I might push that due date out or further just to give you more time to sort it out.
Yes, sir. Thank you.
Yep.